Hi, this is Physics 1, Chapter 4, Part 3, and we have gone through the Newton's first law. We went over free body diagrams, which is going to be very important, and the different kinds of forces. Throughout that, we mentioned that force, and specifically a net force, is related to acceleration. Matter of fact, you can't have an acceleration without a net force. We also noticed that mass and acceleration are related because mass is the resistance to acceleration. And so all of this gets put into a nice little formula called F equals ma. And sometimes you'll see it written as A equals F over m. And so with this formula, we are finding Newton's second law, which is the law of acceleration. An object only goes from rest to motion if there is a force applied to it. So if something's sitting there, it won't stop moving until there's some force that causes it to move. And that means it's going from 0 to some velocity, which requires a force. That change in velocity is what we call acceleration. So for it to have an acceleration, it requires a force. The net force is related to acceleration, so acceleration and net force are proportional to one another. That means that if the acceleration goes up, your force goes up. So if you have a higher acceleration, you have a higher force. If you have a lower acceleration, you have a lower force. Or if you need a lower force, you will need a lower acceleration. Right? So they're proportional to each other. They both move in the same direction, basically, as in increasing or decreasing. So we can look at these diagrams. These are three different diagrams. This one has a normal force pushing up, gravity pushing down. They're equal, so wherever this is, it's on the ground, so it's not going up or down. And then friction is holding it for some reason. And so, if this was at rest, this friction will mean that it will have to be at an angle, but if it's at an angle, the normal force will have to be curved. So there's no way this is at an angle. So what this is something moving at a constant velocity, where its newtons are 40 newtons high, gravity and its weight is 40 newtons down, and then it's, well, it was moving at constant velocity, I should say, then begins to slow down. And so it's braking or slowing down. You got friction causing that, which is 10 newtons. So this one is accelerating. And accelerating to the left. Okay. Object 2, it could just be sitting there. It could be moving at a constant velocity. But these cancel each other out and we have no forces left or right. So it's not accelerating. For 3, you have the L force acting up. You have gravity pulling it down. So this could be somebody parachuting out. They have a weight of 25 newtons. And when they open their parachute, the force pushes them up. And so they go up some. And so yeah, maybe it's not that. Maybe it's more like a balloon. The air is pushing up, gravity's pulling down. You know, so you have accelerating upwards. We already mentioned that inertia is the object's resistance to acceleration. And so it's a resistance to change in motion. So acceleration is related to inertia, which is mass. So mass and acceleration are related. They are inversely proportional to one another, which means a larger mass, you are looking at smaller acceleration. So imagine kicking a couch. You may even get that couch to move a little bit, but it's not going to move a lot. It's going to be a small acceleration. You kick a little tennis ball, it's going to go flying, and it's going to have a large acceleration. So as I said before, acceleration's related to 1 over mass at this point, so we can put this all together and we got acceleration equals the net force over the mass, or A equals F over M. Right, so let's say we have a net force of a 50 kilogram mass going from 0 to 10 meters per second in 2.5 seconds. So we can find the acceleration first. So speed is going to be 10 minus 0 over 2.5. So we get 10 over 2.5, which is going to be 4 meters per second squared. Then we can find the net force. Mass times acceleration. Mass is 50 kilograms. Acceleration is 4 meters per second squared. And so you're looking at a net force equal to 200 newtons. Okay, very simple problem there. What is the acceleration of a 100-gram object being pulled by a 2 Newton force? So we're given the 2 newtons. So we have force in net is m times a. Net force is 2 newtons. Mass is 100 grams. So I'm going to switch that to kilograms, 0.1 kilograms, and solve for A. So A is 2 over 0.1. And you get 20 meters per second squared. Okay. We have objects that are being pushed by 5 newtons force separately. One object accelerates to 0.5 meters per second. The second object accelerates to 2 meters per second. What is the mass of each of these objects? So we're looking at F, I'm going to call it F1 equals M1 times A. F2 equals M2 times A. Right, times, I should say A1 and A2. Okay, both are 5 newtons. We don't know the mass. Acceleration, the first one is 0.5. And the second one is 2. And so when we divide by 0.5, we get M1 equals 10. And these are meters per second in newtons, so it would be 10 kilograms. When we divide by 2, M2 will equal 2.5 kilograms. So the smaller mass had the larger acceleration given that same force. Larger mass, smaller acceleration given this, again, the same force. Next problem. We have a 500 gram object. I don't know why I wrote A. Is being pulled down by the acceleration of gravity, which is 9.8. So acceleration is gravity, which is 9.8 meters per second squared. What is the force on the object due to gravity? Okay, so the net force equals 0.5, that being kilograms, times 9.8, which is going to be 4.9 newtons. This leads us to the next thing, which is called weight. Weight equals force due to gravity. If you know your mass, you know your weight, as long as it's on Earth. If it's not on Earth, it's going to have a different weight, and you have to know that gravity. which we do know other planets, but we don't need to worry about that right now. So, weight is a force, units is newtons, and to find a weight, you just multiply mass times gravity, which is exactly what we did here. Your A is G in this case. We can label it sometimes as W, sometimes as FG, and like I said before, sometimes I just label it as MG. The weight can change without altering the mass. We go to a different planet, you go up in space, you go just really, really high, your weight changes a little bit. The farther you get away from the core of the Earth, you got a little bit less gravity, and it will change your weight without changing your mass. If you become a different weight, you still have the same mass. So you're going to always have the same mass as long as as long as you stay the same size and don't exercise and all that. That's the only way to change your mass is exercising, or not. It's the total opposite of exercising. But your weight and mass, given a specific mass, your mass won't change, but your weight can if you go away from your gravitational force. So for the 1 kilogram mass, your weight's going to be multiplied by 9.8 newtons. This is always meters per second squared. If you have a weight of, let's say, 1 newton, I'm going to hurry up here. It's telling me it's wanting to kick me off. And you want to find your mass, you just divide by G. So you're dividing by 9.8. So 1 newton over 9.8. And we get 0.1 newtons. The last one, 25 kilogram cat. The weight of the cat will be 25 kilograms times 9.8 meters per second squared. And you get 245 newtons. Okay. So we're going to go back to these diagrams. We already knew that certain ones accelerated and certain ones didn't. Now we're going to find the actual acceleration. And all we need is this free body diagram to find it, because we know what the net force is. For object 1, we have a weight of 40 newtons, force of gravity. So if we want to find the mass for object 1, 40 equals mass times 9.8. Divide by 9.8, you get 40 over 9.8. Which is 4.08. Okay. And then if we want to find the acceleration here, well, the acceleration is going to be the net force over the mass. Mass is 4.08. The net force was 10 newtons. Okay, that was the only force in the x direction. There was no net force in the y direction because these two canceled out. And so you get 10 newtons divided by 4.8, or 4.08. And you get 2.45. Now, because this is going to the right, and you probably have an idea that this object is moving to the right, I'm sorry, this is going to the left, the object's moving to the right, we're going to call this negative. So the force is negative, that means your acceleration is going to be negative. So you got 2.45 meters per second squared. Acceleration and force will always be in the same direction, okay? Because they are the only ones that have a direction that mass does not. So if this is positive, this will be positive. If this is negative, this will be negative. Okay, object 2, we had 20 newtons, and it's equal to mass, right, object 2, 1 times 9.8. So the mass here equals 20 divided by 9.8, and you get 2.04 kilograms. Okay. We said before that the net force on this one was 0, so your acceleration is 0 over 2.04, which is 0 meters per second squared. So no acceleration on the second one. Object 3, 25 is the weight, mass times 9.8. So it's going to be a little heavier than the last one. 2.55 is your mass. And so your acceleration is going to be, we said, 15 upwards. Okay, so we're going to count up as positive. So net force was 15, mass is 2.55. You get 5.88 meters per second squared. Let me see where I'm at in time. 60 minutes. Yeah, I'm going to keep going as long as this holds out. Maybe we'll get through Newton's third law before I have to stop it. Okay. The last one, and this really deals with what's called interactions and systems. Right? Two objects exerting forces on each other will exert the same force on each other. So to every action, there's always an opposed equal reaction. So force of 1 on 2 equals a negative force of 2 on 1. We can write this as M1A1 equals negative M2A2. Okay? As long as we're not looking at what's called an external force, which is a force outside of the interaction. So the force on the first object on the second is equal to the opposite in direction to the force on the second object on the first. I wrote first twice. And we want to emphasize it. So the force on the skater on the wall is applied in the direction of the wall. So the skater pushes on the wall pushes back on the skater. So force on the wall equals the force on the skater. Okay, we see this with weight and a normal force. Normal force up, weight is down, and they equal out. So with this, let me give you kind of a scenario here. It's going to be a little funny scenario, but I like this one. You got a bus. Well, this looks more like a train, so we'll say a train. Doesn't matter. Train is moving at a certain speed. So speed equals, I don't know. We'll just say speed equals v. Speed equals v. It has a certain mass. I'm just going to call it big. So it's going to have, as it moves, a bug. Bug's going to have a mass that is, well, equal to little. And it's going to have a speed that's also equal, well, we won't say v2. to V2. Okay, so this bug comes and slams onto the train, or the train slams onto the bug. Doesn't matter. They slam into each other. What happens to the train's speed? Well, there may be some drop in the speed. May be very, very little. Probably need a super, super high-tech equipment to actually find that acceleration. So the acceleration will be extremely small. So we're looking at the mass is big for the train times extremely small acceleration. And that's going to be equal and opposite, because they all go in opposite directions, to the bug, which has a mass that is very little. I guess I want to add a very in. And its acceleration, well, he's pretty much going to go from V2 to 0, which is a high acceleration. It also accounts for the negative sign. It's a high acceleration. So very high acceleration. But they end up equaling each other. And so that's the idea behind Newton's third law. So when we think of a system, we're thinking of isolated events. This would be an isolated event. Another one, if we look at a skydiver, throughout this we'll look at each small interactions. One system may involve the forces on the person while he is in the air, but the chute isn't open yet. The system starts when he leaves the plane and ends when his chute opens. Another system would be the point in time when the chute opens until he lands. A third system is actual landing and interaction of that skydiver with the ground. There's also when he leaves, the interaction between the plane and the skydiver. All of these contain interactions. Each system can have a net force that is 0 or non-zero. When a system has a non-zero net force, that is considered external force. Right, so, for example, we have a book on the table. This is the system here, but if you push this whole table, this table and book could accelerate, and that's your external force. Which I mentioned again, the book on the table. So every force is a part of interaction. Skydiver jumps off the plane, interaction between the plane and the skydiver. Skydiver chute opens, there's an interaction between the chute and the skydiver. The skydiver lands, there's an interaction between the land and the skydiver. In all these interactions, you'll have equal forces equal in magnitude, opposite in direction. Alright, so certain forces really take this into account. I already mentioned this, so I'm not going to mention that book again. These forces are called reaction forces. First one I just mentioned above, the normal force. That's always the reaction force to something sitting on the surface, as much as it can. So like I said with the car, if the car is sitting on a table, that table can't hold the car, and so it can apply as much of a normal force as it can, but it's going to get squashed. And the acceleration of the car breaking through that table is going to account for that high normal force, but it still won't be enough. Otherwise, if you have the table, there's no normal force there. Friction is another reaction force. This is a force that interacts with objects rolling across the surface and stops the objects before hitting anything else. It's also the force that that maybe hold something onto a surface where the surface may be inclined. It always opposes motion or possible motion. Now, I've mentioned these before in the last video, but I do want to go a little bit more into detail with them. Static friction. This is the friction that holds something in place when there is a force trying to move it. We write what's called a coefficient of static friction. And what that is it basically it's a percentage. So there's no units on it. It's a percentage of the normal force that's going to be applying this static friction. So the equation for it is Fs equals mu s times the normal force. And so we see here this person is able to stand up on this based on friction and the fact that you have the normal force pushing off on them. Then we have the kinetic friction. This is friction on something while it is moving. This is a friction that stops a rolling object. It has a coefficient called kinetic friction, which we write as mu sub k. The kinetic friction is found by friction k equals mu sub k times the normal force. So if we look at this and we start applying a force, and as we apply a force, friction applies a bigger force. So let's say we are moving that big cherry dresser, and we're trying to push on it. Okay? There's going to be friction that's going to be pushing back. It's going to be static friction. So we try a little force, we apply a little bit, friction applies a little bit back. Apply a little bit more, friction applies a little bit more back. Apply a little bit more, friction applies a little bit more back. Until it gets to the point where we applied so much friction that this friction can't apply anymore. Then this is when the dresser starts to move, and it drops down to kinetic friction. And as we move this dresser, kinetic friction then is slowing it down so it doesn't go shooting across, but it stays constant. And that's when the object starts to slide. And then when we come to a stop by getting tired, we'll back down to 0 again. Take a look. Okay. Alright, so I'm going to finish Hooke's law, and then I'm going to start the next video after I charge my computer. Hooke's law deals with elastic material. There are another reaction force. Elastic material meaning materials that can stretch and compress. Springs, rubber bands. So here's a normal spring, has an equilibrium position where it sits. You pull it out, it applies a force to want to pull it back in. You push it in, it applies a force wanting to push your hand out. Okay, so the spring force opposes any applied force, and we write this as F equals negative K. Well, K is the measure of elasticity, so it's the measure of how much an object shape changes when a force is applied. And basically, it's a rate of change per force. And then, so force is negative K times your change in distance. That's how much you compress it or stretch it. So we stretch a spring that is 2 centimeters. So delta X equals 2 centimeters. But we're taking the spring and we're pulling it out. So there's applied force. And this K for the spring is 40 newtons per meter. So K equals 40 newtons per meter. The force that we are applying to this is going to be equal to 40 times 0.02. Which is 0.8. The spring force, which is the force that's opposing this, is going to be equal to negative 40 times 0.02, which is going to be negative 0.8. And so it counters your applied force. Now, if you pull hard enough, the spring force has a limit and will break. And we actually, when we get into elastic materials, actually we won't get into it, but there was engineering classes that do. I took engineering materials that did. They talk about different phases of it where you apply high enough force. I'll probably mention this if we have an actual class lab with springs. Don't apply too much force because you start to elongate the spring, and it goes through kind of changes where it can't come back. And then if you apply really too much force, you can break the thing. Okay, so this is going to be not too long a video, but I'll start the next video after I charge my computer, and I'll be doing some of the force problems here. We'll get into some smaller ones that are just based on diagrams, and then we get into actual some problems with that involve forces. And there's a few, and then this is going to be one of the biggest ones, that we deal with a ramp. And you can see here, this may look a little strange, but this is a big part of it. Okay, so I'll see you in the next video.